Welcome to AI Paper Slop. Today we are looking at a paper from researchers at KAST and Never AI Lab called WorldKV, Efficient World Memory with World Retrieval and Compression.
Yeah, this is a massive one for anyone building interactive video generation.
Right, because right now the biggest bottleneck in autoregressive AI world models is basically amnesia. Like, you walk out of a virtual room, you turn around to go back inside, and the entire room has just vanished.
Replaced by some totally hallucinated, procedurally generated brick wall or something.
Exactly. And it happens because when a video diffusion model looks away from a scene, its KV cache gets evicted just to save memory.
Just dumps it.
Yeah. But WorldKV actually cures this amnesia completely, and it does it without retraining a single layer of the model.
Which is the crazy part.
It really is. It basically intercepts those evicted caches, saves them into CPU or GPU memory, and then compresses them by pruning redundant tokens based on key similarity. And then it just natively retrieves them the exact moment the camera returns to the scene. So you get real-time AI world models with persistent long-term memory.
While actually maintaining your real-time frame rates.
Yes, exactly.
It fundamentally changes the math here. We are looking at perfect memory retention without paying that standard, usually crippling inference tax to get it.
Right.
By treating the cache as an addressable database rather than just, disposable scratchpad data, the bottleneck just disappears.
Yeah. But before we get into the mechanics of how they actually pull that off, we should probably establish why this bottleneck even exists for engineers building these systems.
Yeah, for sure.
Because for anyone whose hands aren't, dipping the code every day, the KV cache, the key value cache, is essentially the model's scratchpad.
Exactly.
It's where the model stores the mathematical representations of the tokens it has already processed, so it doesn't have to recalculate the visual features for every single frame from scratch.
Right, because doing that would just be impossible computationally. Right. We were talking about engines like Matrix-Game-2.0 and LingBot-World-Fast.
Yeah.
And these are trying to generate real-time environments for gaming or robotic simulation. Generating plausible frames right in front of the camera, that's kind of a solved problem now.
When next frame is easy.
Right. But the holy grail is a persistent, explorable world. Like if an embodied AI agent leaves a kitchen, walks down a hallway, and then turns around to go back.
The kitchen needs to actually be there.
Yes. It needs to retain its exact spatial geometry, the lighting, the objects on the counter. Everything has to be exactly as you left it.
But if you're building an AI world model, you're forced into this brutal trade-off right now. Like, option A is using what's called full KV cache attention.
Which gives you perfect memory.
Right, because the model is attending to every single token it has ever generated since the simulation started. But over just a 1-minute rollout at a decent frame rate,
you are accumulating hundreds of thousands of tokens.
Exactly, hundreds of thousands. So your GPU VRAM maxes out instantly, and the inference speed absolutely plummets.
And that drop in throughput just destroys the utility of the model entirely.
Yeah.
If you run full KV cache attention on LingBot-World-Fast, the frames per second drop from about 8.87 down to 3.61.
Wow.
Over just a single minute of generation.
Yeah, that's totally unplayable.
Completely. Real-time constraints are immediately broken because the self-attention mechanism is, performing these quadratic calculations across a constantly exploding number of tokens.
Right. So to avoid melting the GPU, engineers pivot to option B, which is sliding window inference.
Right.
You basically cap the context window to, say, a few dozen frames. You get your speed back, but the moment the agent turns around to re-enter that kitchen, the model hallucinates completely new content.
Or the geometry severely drifts.
Yeah, because the context from the original scene was just pushed out of the sliding window and totally evicted. I kind of think of it like a video game engine aggressively culling assets behind the player to save RAM.
Yeah, which is standard practice in traditional gaming.
Right, but the difference is, when the player turns around in this AI setup, the engine procedurally generates a completely new room instead of loading the old one from a hard drive.
Exactly. The eviction that guarantees your real-time attention cost is the exact mechanism that destroys the long-term memory.
Yeah.
And historically, the field has attempted to fix this hallucination problem by basically building external memory banks on top of the base model.
Right, systems like RELIC or Gen 3C.
Yeah, those require training dedicated memory modules, or introducing explicit 3D scene representations that condition the video model on, like rendered views of a reconstructed geometry.
So you're essentially duct taping a complex memory system onto the model.
Pretty much.
And that requires heavy fine-tuning and adds this massive reconstruction latency at inference time. But what makes this case in Naver paper so fascinating is they realized we don't actually need any of that.
Yeah.
They noticed something just hiding in plain sight. They discovered the KV cache already functions as an emergent form of long-term visual memory.
Which is wild. We saw hints of this previously, where attending to the full history of KV caches maintained consistency.
Right.
But earlier models were trained on minute-level videos, so the assumption was that long-term memory was just a learned behavior explicitly baked into the training data.
Ah, I see.
But this paper proves the phenomenon is fundamental to the transformer architecture itself.
Yeah, because they tested this on Matrix-Game-2.0, right?
Yeah.
And that model was only trained on incredibly short sequences using just a 6-frame sliding window.
Exactly.
So if a model was only ever trained to look 6 frames into the past, how on earth does it know what happened 600 frames ago? Like, it literally shouldn't have the capacity for long-term consistency.
It shouldn't, but it comes down to the nature of self-attention. Even when it's predicting just the next few frames, the attention layers have to learn rigid spatial consistency to accurately predict how pixels shift and occlude each other.
Oh, interesting.
Yeah, so to get those short 6 frames right, the model inadvertently builds a holistic, 3D-aware world state in its internal representations.
Just as a byproduct.
Pure byproduct. Oh. So if you remove that sliding window restriction at inference time and force Matrix-Game-2.0 to attend to its entire KV cache history, it perfectly reproduces previously seen viewpoints.
That's amazing.
The memory isn't trained into a specific module at all. It is natively emergent within the spatial features of cache.
Okay, so we have this gold mine of memory already sitting there. The model inherently knows the geometry of the room,
Right.
but accessing it requires full attention, which, as we established, melts the GPU. So how do we actually get the data without that catastrophic compute cost?
By entirely rethinking the life cycle of the KV cache. Under standard sliding window inference, evicted chunks are just thrown in the trash, right?
Yeah.
Well, the first component of WorldKV, which they call World Retrieval, just stops that deletion. Instead of discarding evicted chunks, they are sent off to GPU or CPU memory for cold storage.
Right. It's like having a massive archival filing cabinet in the basement, which would be your CPU RAM. And the physical desk you're working at is the GPU.
I like that analogy.
You cannot fit the entire filing cabinet on your desk. That would be full KV cache attention, and the desk would literally collapse.
Exactly.
But you also don't want to throw old files in the incinerator, which is what sliding window inference does.
Right. So to manage what actually goes on the desk, they structure the active sliding window very deliberately.
How so?
They use an 18-frame sliding window, and it's partitioned into 4 specific regions.
Okay.
First, you have the sync chunks. That's the initial 3 frames of the entire generation, acting as a foundational visual anchor for the sequence.
Got it.
Then, the retrieval chunks, which is a 9-frame window, specifically reserved for fetching those memories up from the basement.
The archived files.
Right. Next are the recent chunks. That's just the 3 frames immediately preceding the current moment. And finally, the denoising chunk, the 3 frames actively being generated.
Okay, so the structure makes sense. But if I have thousands of evicted chunks sitting in cold storage in the basement, how does the system possibly know which folders to pull up into that 9-frame retrieval window?
View-dependent retrieval.
Right.
Every time a KV cache chunk is evicted and stored, it is indexed by the camera or action state at the exact time it was generated.
Oh, that's smart.
Yeah. When generating a new frame, the system calculates the relevance of your current camera state against all the stored states. For a model like LingBot-World-Fast, where perfect 3D camera poses are available, it actually computes a combined distance.
Like mathematical distance.
Exactly, using the squared L2 distance in translation and the geodesic distance in rotation.
So it mathematically calculates the physical distance between where your current camera is and where the camera was when that old cache was generated.
Yep.
And then it just finds the top most relevant chunks that match your viewpoint and slots them back into the attention window.
Natively. No re-encoding, no architectural changes at all. It just drops the raw cache back in.
Okay, but wait. What about Matrix-Game-2.0? A game engine just takes discrete keyboard inputs, like WASD for movement and mouse movements for looking around.
Right.
A keyboard press is not a 3D coordinate. How does a simple key press map to a spatial query that actually matches a 3D visual token?
This is where it gets really clever. It uses pseudo-trajectories.
Pseudo-trajectory.
Yeah. When you press W to walk forward, the framework logs that temporal action. It accumulates those discrete WASD and mouse-yaw and pitch commands into pseudo-translation and pseudo-rotation vectors.
Oh, I see.
It essentially says the user moved forward for 10 time steps, then rotated 45 degrees. By mathematically reversing that trajectory when you turn around and walk back, the system calculates a coordinate that matches the exact timestamp of the evicted cache.
That is brilliant.
Right. Even though these vectors aren't perfectly calibrated to an explicit 3D mesh, they capture the relative motion of the camera perfectly enough to pull the visual features from the exact moment you were standing in that spot.
Okay, but hold on. Pulling the right folders from the basement into a 9-frame window on the desk creates a massive spatial bottleneck.
How do you mean?
Well, if each chunk we retrieve is 3 frames long, our 9-frame budget only lets us look at 3 discrete chunks from the past.
Right.
If we try to look at more history to maintain a really complex room, we will just max out the active window and hit an out-of-memory error anyway.
Which necessitates the second core component of this paper, world compression.
Ah, okay.
The researchers understood that adjacent frames in a video are highly, highly redundant. If you are looking at a mostly static background wall, you are storing the exact same visual features in the KV cache 3 separate times within a single 3-frame chunk.
Sure, but why not just aggressively downsample the resolution of the retrieved chunks or, lower the frame rate before putting them in the window? That would save space immediately.
Because aggressive downsampling destroys the high-frequency details that make the generated world look consistent.
Oh, right.
You lose the fine texture of a rug or the sharp geometry of a window frame. When the model tries to generate the room again, it uses that blurred, downsampled cache as a reference.
Which would just result in severe geometry drift.
Exactly. So instead of lowering resolution, world compression targets redundancy at the token level using key-key similarity.
Okay, let's get under the hood of key-key similarity for a second. In a diffusion transformer, the keys essentially encode the spatiotemporal correspondence of the visual features.
Right.
The model uses keys to figure out where things are and how they relate to each other.
Exactly. So within a 3-frame chunk, the system designates the first frame as the anchor frame. It keeps that anchor frame completely intact, preserving 100% of its token.
Makes sense.
Then it takes the keys from the second and third frames and calculates their cosine similarity against the keys of that anchor frame.
So if the cosine similarity is exceptionally high, it just means that specific token in frame 2 is functionally identical to what is already sitting in the anchor frame.
And if it is identical, the system prunes it. It completely deletes the token.
Wow, just trashes it.
Crashes it. It only retains the tokens with low similarity, meaning they carry distinctive, new spatial or temporal information.
Okay.
In practice, they retain only about 25% of the tokens in those non-anchor frames.
Wait, isn't deleting 75% of the visual data from the subsequent frames exactly what we're trying to avoid?
It sounds like it, yeah.
I mean, the entire goal is to prevent amnesia. If you just trash 3/4 of the tokens, won't the model just hallucinate the missing details when we try to reload the room?
No, it doesn't hallucinate because of what actually survives the pruning. The 25% that remains contains the only genuinely new information generated in that time step.
Oh, I see.
When you look at the visualizations provided in the paper, the low similarity tokens map perfectly to newly revealed spatial areas.
It's like when turning a corner.
Exactly.
Yeah.
If you are turning the camera to the right, the surviving tokens are heavily clustered along the right edge of the screen where new environment is coming into view. Everything to the left is just a translated version of the anchor frame, so it gets pruned.
So it basically isolates the delta between the frames.
Yes, exactly.
The paper actually has this brilliant example of a scene with a windmill in the background.
Oh yeah, that's a great one.
The camera is moving backwards, so the surviving tokens highlight the edges of the screen as the field of view expands. But the surviving tokens also perfectly highlight the rotating blades of the windmill.
Right, because the blades are dynamic. The windmill structure is in the anchor frame, but the physical position of the blades in frame 2 has changed.
Ah, so their keys are different.
Yep, the cosine similarity drops, and the system knows to save those specific tokens because they represent dynamic temporal data.
That is incredibly elegant. So you have the full anchor frame plus 25% of frame 2 plus 25% of frame 3. You essentially compress a 3-frame chunk down to the equivalent memory size of 1.5 frames.
Right, and your 9-frame retrieval budget can suddenly hold twice as much historical context.
Because you fetch 6 compressed chunks instead of 3 uncompressed ones.
Exactly. Doubling your memory capacity under the exact same VRAM constraints.
That's huge.
And this compression happens independently per layer at storage time, which is a really vital architectural detail.
Why does it matter that it's per layer?
Because in a deep network, different layers value different distinctive tokens. A shallow layer tracks low-level textures and edges, while a deeper layer tracks high-level semantic objects.
Oh, of course.
If you force a uniform pruning mask across all layers based on a single similarity score, you just destroy the functional integrity of the cache. By computing the key similarity and pruning independently per layer, every layer retains its own specialized set of distinctive tokens.
Okay, so we have world retrieval fetching the right memories based on pseudo-trajectories or camera position, and world compression having the size of those memories by pruning redundant tokens based on independent layer similarity.
Exactly.
And this entirely training-free framework operates purely at inference time.
Yes.
So when they actually run the benchmark, does this hold up in a complex simulation?
Oh, absolutely. They built a really rigorous benchmark of 60 scene trajectory pairs covering diverse domains like indoor rooms, urban environments, and natural landscapes.
Nice.
They designed long horizon trajectories, specifically featuring repetitive revisits, forward-backward traversals, and complex loop closure events where, the camera navigates a long path and then returns to a starting viewpoint.
The ultimate stress test for Amnesia.
Exactly. And across these tests, on both Matrix-Game-2.0 and LingBot-World-Fast, WorldKV doesn't just match the memory fidelity of the computationally massive full KV cache attention.
Wait, it doesn't?
No, it frequently surpasses it.
Okay, I am still struggling with that a bit. How can a compressed, retrieved subset of data possibly produce a better, more consistent image than the entire uncompressed history?
It seems counterintuitive, I know.
Because full KV cache has access to every single piece of data ever generated in the sequence. It should theoretically be perfect.
It comes down to the signal-to-noise ratio within the attention mechanism itself. By pruning the redundant tokens, WorldKV provides a much cleaner, effective context for the attention layers. When you feed a model the full KV cache, the attention mechanism has to sift through hundreds of thousands of highly redundant tokens.
So the calculation gets noisy.
Really noisy.
Yeah.
The attention weights get heavily diluted because they are being spread across hundreds of near-duplicate background walls.
It's like if I give you a 3-page summary of a meeting that only contains the actionable points, you will execute the plan perfectly.
Right.
But if I give you a 500-page unedited transcript of everyone clearing their throats, repeating themselves, and going on tangents, the critical information gets diluted and you miss the actual point.
That's a perfect analogy. By stripping out those redundant tokens, world compression sharpens the attention signal. And because the chunks are drastically smaller, world retrieval packs more distinct historical viewpoints into the same 9-frame budget.
Because you have more room on the desk.
Exactly. You provide the model with a wider diversity of relevant past views, containing far less redundant noise. This translates to better PSNR, or peak signal-to-noise ratio, and higher structural similarity index scores.
Which means the actual image quality is just better.
It is. It also achieves lower LPIPS and FID scores, proving that perceptual distance and image quality are superior.
This represents a massive win for engineers doing this deep dive into real-time environments.
Totally.
You get better memory fidelity, a cleaner attention context, and you maintain roughly 2 times the throughput of full KV attention, preserving your real-time frame rates.
And you just bolt this KV cache management framework onto your existing sliding window inference pipeline.
Without having to retrain a massive foundational model.
Or maintain heavy, explicit 3D meshes in the background. It lowers the barrier to entry for persistent interactive worlds completely. The memory is already embedded in the spatial representations of the cache.
We just needed a more intelligent filing system to organize, compress, and retrieve it when the camera turns around.
That's exactly it.
Which brings up a profound implication for you to mull over as you work with your own autoregressive models. If KV caches naturally develop intricate spatial world memory, just as a byproduct of trying to predict pixels on short 6-frame clips, what other implicit physical laws are hiding in the caches of current architectures, just waiting for the right retrieval mechanism to unlock them? Are we just scratching the surface of what these models inherently know about 3D space?